Okay, so for today, you will say are relying on your classmates here, okay, to go over what you may think is possibly needs a little more clarification or what you might have problems with. Okay, so some of the things that we approach these problems is the first thing, we want to know the substance. What would you ask about that? Well, true, you would say, what is it? But can we just tell me? Is it a known substance or is it unknown? Okay. Then you want to try to answer what the question is asking. So, if you are trying to solve for heat, that can be what? Labels. Okay, so here's your heat values, joules or kilojoules. And you have this wrote down already. It's not like you have to write this down again unless you feel it's absolutely necessary. This variable, C with a subscript of P, is what? That's a specific heat. And how do you label any specific heat? Joules over grams in degrees Celsius. One way to look at that is just a rate for the size of that substance. For every temperature increment that it is rising, it takes a specific amount of heat, which of course we know is measured in joules. Okay? Then, if you have a really good understanding of this, what are probably two important variables that we are missing yet? Okay, so if something is measured in kilojoules over moles is one way. And there's another way we can label this. Joules over grams. And both of these are illustrating a what? Not quite. It's either heat of fusion or what? Yeah, it's either heat of fusion or a heat of vaporization, okay? So, yes, there's other problems that we had talked about, but a lot of that is going to be a review. Because if you are looking for the mass of a substance, it's going to be measured in what?
Grams.
Okay, or kilograms, which chances are it's just grams, okay? And if you are looking for a molar mass of a substance, that's measured in what? Close, that's half of it. What is a molar mass labeled in? Going all the way back to last August and September. If we're looking for some object's molar mass, how do we label that? Mole is part of it. I think I heard it. I don't know. Yeah, grams over moles. That is a molar mass, okay? Because probably what gets to be so confusing about that is it's called a molar mass, but typically that's how we utilize it, but it can also be moles over grams, okay? Hence a molar mass. All right. So is there any specific topic, question, whatever it is that you might want to discuss? Thank you. For those of you tuning in, I had a special delivery, so I was probably supposed to get down to the office to pick up a package a while ago, but thank you, Miss Tiffany. Is there anything that you struggle at the most? Okay, I hear 5-step problems. Anything else? Probably one aspect, I'll try to point you into the right direction. Some questions might ask how much energy would be required to raise the temperature from an object's or up to an object's melting point. If it's starting at 20 degrees centigrade. So what that would mean is, keep in mind what we just said. How much heat? So we already know what variable are we trying to solve for when we say how much heat. Okay, so it's either going to be joules or kilojoules. Okay, so when we say how much heat is needed to, let's say, raise, okay, need an element then. Something we use iron a lot, and we use aluminum. Zinc we haven't used before. Okay, how much heat is needed to raise? So how much of this zinc do we have? Over 400 grams. 400 what?
406.
Okay, so 400 grams of zinc from, I don't know, we said 20 earlier, so 20 degrees centigrade to, I don't know, well, we really need to melt this zinc, so I'm just going to speculate. I'm going to say 2720 degrees centigrade. Okay? So when we approach this like what we said earlier, you read the problem, the first thing we said, is this a known or an unknown substance? Well, it's known because we say that it's zinc, okay? And when we say how much heat, we know that's going to be measured in probably this, okay? Or you can do this, kilojoules, one or the other, okay? Those are both measurements of heat, okay? And one thing to keep in mind, this is a big clue right here. Because what variable might that resemble when you see that? Notice I said one variable, but we're looking at two numbers. So what about temperature, though? You're not wrong. Yes. Okay, triangle or temperature final minus temperature initial. So keep in mind, this is not cooling down, because if we want to know how much heat is released, we would say from 2720 degrees centigrade to 20. Okay, so in the top example, it gives you a positive value. In this example, it gives you a negative value, which it can. Okay. Is anyone confused about that, on why or how you get a positive value for this? Okay, just remember it's temperature final minus temperature initial. So 20 from here gives you 2700, but 2720 all the way down to 20 is going to give you negative 2700. Okay. So it's not that heat is negative, it just means that it's released. Just like when you are about a quarter of a mile away from a stop sign, you take your foot off of, you could say, the gas pedal, the accelerator, whatever. It just means you're starting to slow down. Same concept, you're just releasing heat in this bottom example. Okay. So what variable do you think we are missing? Because this happens at a specific rate. We need to know what the specific heat of zinc is. Oh, it's not on there. Okay, so we will extrapolate by looking at what iron is, and that is 0.445, I think. So since it's 3 doors down, and it's a little heavier, so I think it would take a little more. We're going to say 0.490. So the specific heat is 0.490 joules per gram degrees Celsius. Okay. So do we need to know the heat of fusion or heat of vaporization for this? No, we do not. If you have a good understanding, you can tell me why. We're just heating it up, yeah. We're not worried about all the different types of phases that it's going to go through, okay? So in this case, here's a clue. What formula would we use for this? The quantity of heat will equal the what times what times what?
Mass times specific heat.
Okay. So the mass we said was 406. Okay. The specific heat was determined to be 0.490, and then temperature final minus temperature initial gives you 27 what?
100.
So two what? Zeros? Or O's or ooh. Okay? Yeah, I'll fall into your trap. Okay? Yeah. Oh, depends how you look at it. Yeah, it's really not funny. Yeah, it's 2700, not 2700. 2700. Okay? So you're all competent enough. You know how to use a calculator. So for those of you tuning in, you're just multiplying those, and that's what you have. Okay? Questions over something like this? Rut row.
What if you don't have joules over grams and you have kilojoules over joules?
That's an altogether different problem. We're going to jump into that next. So rut row with this. Can we just make a presumption? Okay. Okay. Second row. Third row. Now, for some of us, I saw both expressions. Okay. Sorry, are we good? Okay. All right. So going back to your question, okay? And that was, well, why doesn't it say anything about a heat of fusion in there? Well, here's why. Okay? We'll stick with the same substance, okay? And we're not worried about a temperature range anymore. So we can get rid of this substance or variables, okay? So how much heat is needed to raise 406 grams of zinc? We would say to melt the substance. Okay? And for some of you, I made this specific comment because you would put these diagrams on here, and I said, you're already 5 steps ahead. Well, I don't know if it was 5, but you're already multiple steps ahead of everybody else, because what you're doing when you draw this, you are saying, I have a good understanding of this, which you do, okay? And what that means is, there was step 1, step 2, step 3, step 4, step 5. The prior example we did was just like, for instance, step 1, because that was Q equals mass times specific heat times change in temperature, because it gave you a temperature range, okay? But what happens from here to here, now the individuals that answered this are not in here, so we'll see who's actually paying attention. What is significant on this line, right? Or this one? What's happening? Well, you're not wrong. Just tell me. Right, but it is a heat of fusion or heat of vaporization, but what is not happening? That's the more important question. Something's not changing. Yeah, the temperature is not changing, okay? So in this case, this is similar to this step here or this step here. You're not worried about whether the temperature is changing or not. You just want to get it up to its melting point. So we're not even concerned about the melting point. So we do need one more variable. And what would that possibly be? Not the melting point. Not the boiling point. Now remember, raising it to its melting point, or that's a clue right there, we hope. Because what's happening in this step here? You're not adding heat, so what's starting to happen to this zinc, because we're already past its melting point? Yeah, we need a heat of fusion because it's starting to melt, okay? So in this step, you just have Q equals mass times whatever that object's heat of fusion is, okay? Then in this one, you just have Q equals the mass times its heat of vaporization. I think that shows up on, I know there's a little bit of a glare there, but I think we can sort that out. So in this case, okay, this is where you would have to have this on your table, which you do not have because I never copied off that third page. Darn it. My mistake, your fault. Okay? I am glad we have a sense of humor. Very good. Okay? So, zinc. Has a heat of fusion okay, I gotta find it on here. Okay. Yeah, I thought it would be much higher than that. 7.32 kilojoules. Oh, I'm looking at the wrong column. Kilojoules per mole. Okay. So 7.32. Okay. So it's not that you can't use kilojoules per mole. You can, but there's an extra added step in there regardless because this is a known substance. So how many of you want to use joules per gram? Okay? And you're not wrong whether you choose to do that or not, because in these 5-step problems, you have to have it in joules per gram. Okay? So if you choose not to, that's fine, but we're going to show it both ways. Okay? So first of all, how would we convert that to joules per gram? Because it's something you need to know how to do anyway. Because remember, we want to get this label. So we're close. Okay? Now, that's not to say that you have to do it this way. This is how it works best for me to explain this to you. Okay? Because I don't know what's going to happen 1 and 2 years from now for those of you sitting in a lecture hall with maybe 200 to 300 other students in a general chemistry class, because that's typically how big it's probably going to be down in Vermilion or Brookings. And that's probably an example that you maybe didn't want to hear, but I sure hope I turned, yep, I did turn it on. Wouldn't that stink? Okay, but that's probably what's going to happen. Even down the road at Dakota State, those chemistry classes are somewhere around 75 to 100, so there's quite a few in there, okay? And how that's going to be administered to you, I don't know. But we're trying to put you in the best possible case to be successful. Okay, so do you want to get rid of the mole or the kilojoule first? It doesn't matter. Okay, how can we do that? So here's your kilojoules per mole. So you said you want to get rid of the mole. That's fine. And anything that's measured in a mole over a gram is that object's what? Yeah, more importantly, not just its atomic mass. It's molar mass. Yes, Moles over grams. So this is what, 65 something? 65 point, okay, 58? 38. Okay, so these moles are gone. We've got kilojoules per gram, so we got our gram now. We just get this kilojoule gone. For every 1,000 joules, you have a kilojoule. We now have our joules per gram. So 7,320, that's what we get by multiplying those, and divide by 65.38. Okay, so 7,320 divided by 65.38. 111.96 joules per gram. Okay? So now you might ask, well, I like this variable here. I don't want to convert it to joules per gram. Okay? Well, we're going to do something very similar, and we should get, I shouldn't say it will look similar, and we should get an answer comparable to that. Okay, so what happens then, we're not doing any conversions here. Our mass is still the same, 406 grams of zinc, okay? Okay, so remember when we're saying heat, it has to be joules or kilojoules. We need to get rid of that gram. Okay, so 65.38 grams of zinc would give us a mole of zinc. Okay, so we've canceled those out. We've got this mole on top. Okay, so we have to get rid of that now. Okay, so we can put moles of zinc on the bottom. And then what would we put on top? Well, yeah, 7.32. Yeah. Okay. So there's our kilojoule over mole. So then, once we do this, okay, we're going to take 406 times 7.32, and then we're going to divide that by 65.38, and that gives us, 45.46. 45.46, but that's in kilojoules. I did something wrong here. I'm going to hit pause here for just a moment. Okay, sorry for the confusion there. What happened is I forgot to multiply by the mass that we started with. So should you decide to go to joules per gram, you're taking the mass times the heat of fusion. Well, here we calculated the heat of fusion as 111.96. So if you take it times the mass, you get 45,455 joules. If you want to be one of these individuals here, you're going to get 45.46 kilojoules. And then notice the only difference is these are much bigger, so you'd have to divide by 1,000. So 1, 2, 3. So you do get the same answer. It's just a different way of getting there. Okay? So this is not, if you have a set way that you want to do this, stick to that. Don't get these two intertwined. Okay? So, row. Second row. Third row. Your lab partner. okay? But keep in mind, when you're doing these 5-step problems, can you do this, kilojoules per mole? No, you cannot. Why? Because everything else is measured in joules, because you can't use kilojoules for that. Okay. So I'm not used to doing these problems like this because I just like to remain consistent. So I always convert them to joules per gram first. But either way, some of you have done that when you're labeling heat. You just do it in kilojoules, and that's fine. Okay. Then, we got 15 minutes yet. Trying to keep this short. I think that's what I want to say. Okay, so how do you label heat of fusion? Joules per mole or joules per gram? So notice, if you read this problem, is this a known or an unknown substance? It's a known substance. And you already elaborated, this is what we need. Kilojoules per mole is a heat of fusion, or so is joules per gram. So what you can do, so how many grams of this sodium chloride do we have? It's over 10,000.
37,432.
You said 20, you said 37. That's a difference of 17, so that's 29 and a half.
There we go. All right. That works. Yeah.
Oops. Okay. So keep in mind, the first thing that we need to do, we need to change this grams to, this is two totally separate problems, okay? Because it might say the first thing you need to do is find how many moles are there. And how do we do that? Okay, so 29,500 grams of sodium chloride. Okay, so how do we get this into moles?
Divide by the mass on the bottom.
Okay.
I don't know what the
So let's see here. Chlorine is 35. This is 23. Is that 61? No. $58.45. Okay, so 29,500. Divided by 58.45. That gives us 504.70 moles of sodium chloride. Okay? But how much of that heat was released of this known substance? Why is that important? So how are we going to get moles in this to give us kilojoules per mole? What is this telling you to do here? Okay, exactly what you just said. Take kilojoules, divide by your moles, which means 400 divided by 504. Okay, and this is kilojoules, this is mole, so anything we get from dividing that is going to be in kilojoules per mole. Kilojoules per mole, 0.79. Now, if you looked up the heat of fusion for sodium chloride, I don't know if that's the value you're going to get, but this is just an example of how you would solve for that. Okay? We have enough time to discuss a 5-step problem, or are we good with that? You tell me. Row, are we good? Second row. Third row. Now let's not get to tomorrow's evaluation. Go, I don't know how to do these 5-step problems. Okay? But probably the biggest mistake is made in step 3. Okay? Put these in order. Okay? I understand you're going to get the same answer, but put them in order how you would go about solving for that. Okay? Because what's the biggest mistake made in step 3? Why don't you just tell me so we'll both know?
Subtracting the wrong temperatures.
Right, so what do you need to do in step 3?
Write it out.
True, write it out.
Boiling point from your milk.
Yeah, boiling point from melting point. Because in step 1, okay,
Subtracting melting point from your boiling point.
you're going to take your melting point is your final minus where you started initially, initial point. In step 3, it's going to be your boiling point minus your melting point. Then in step 5, it's going to be your ending point minus your boiling point. Okay? So to make sense of that, where are these numbers coming from? Well, okay, we can use ice as an example. Okay? So maybe you started at 7 degrees. Okay? -7 Celsius. Yep.
Fahrenheit would have been all right.
Yeah, Fahrenheit would have been all right. Then here it's 100 minus 0. And then with this one, maybe it's somewhere around 140 minus 100. That's an example of those temperature ranges. Usually this one is the place where people make a mistake. The boiling point minus the melting point. Okay, so should we not be here on Wednesday? Mother Nature sometimes likes to intercede with that. We will start your final chapter, which is a mixture of organic and biochemistry is involved in that. We start talking about sugars a little bit and amino acids. That is the biochemistry portion. Otherwise, the rest of it is just how many of you can name, we'll go 5 alkanes.
No.
Just give me 5 alkanes that you should remember from physical science.
That was 3 years ago. Dude.
I know it was 3 years ago. Nope.
That's an element.
Nope.
Sorry. I don't know him.
Come on, don't let us down.
You did one, huh? I don't know. I know it's not an element.
You know the answer to this.
Probably.
Just need to think.
Just don't know it.
Butane.
Butane is one.
Oh, propane.
Propane,
Methane.
methane, ethane, pentane. See, you did the first 5.
Oh man.
Okay, then it's hexane, heptane, octane, nonane, and decane are the last 5. Okay, So tune into the Science Channel. Should we not be here on Wednesday, let's hope we're here on tomorrow so we can get this out of the way and make our final approach. We'll catch up to you next time.